Good morning, everyone. I'm Abhishek. I will be presenting Quiver, an informed storage cache for deep learning. This work is done in collaboration with Muthian and Sivathanu from Microsoft Research India. Deep learning is becoming an increasingly important workload. It already powers many real-world applications that we use every day, like voice assistants and web search. This workload is highly compute intensive. It typically involves a machine with expensive hardware like GPUs, which usually have thousands of cores. The machine then reads labeled training data from a store and then sorry, the slideshow is, yeah. The machine then reads data from the storage and processes it on the GPUs. People usually rent virtual machines with GPU on the cloud and to run this workload because buying such a hardware would be very expensive. The data used to train such workload will also be stored on the same cloud like AWS S3 or Azure Blob Storage. The VMs then read data from these services and process it on the virtual machines. The GPUs on these virtual machines can process data at a very high rate, and this places a lot of bandwidth demand on the remote storage. Now let's look at an example. ResNet 50 on ImageNet dataset is a popular workload in computer vision. This model can process around 10,500 images per second on 8 NVIDIA V100 GPUs. Assuming 200 KB per image, this roughly translates to 2 gigabytes per second. And this is excessive bandwidth load on a lot of storage services. So newer hardware like TPUs and graph core are only pushing this limit higher. Therefore, the bandwidth demand will be much more than 2 gigabytes per second. So on top of this, another common scenario in deep learning is hyperparameter tuning, where people launch hundreds of jobs of same model consuming the same data set. So for all these reasons, there will be excessive demand on two components of the data center infrastructure. Number one, there will be a lot of load on the storage services and the storage devices, and there will be a lot of bandwidth demand on the networking part of the data center as well. So an obvious solution one could think of is to just preload the entire data set on the SSDs of these virtual machines and then start the training jobs. However, this is not pragmatic for two reasons. Number one, many cloud providers offer preemptible virtual machines, which are much cheaper than dedicated virtual machines. And these virtual machines can be preempted at any time, and your job will be migrated to a different virtual machine with different SSD with no state maintained. The second reason is the size of the data sets. Some data sets are so large that they won't be able to fit on a single SSD. So for all these reasons, the GPUs on these virtual machines end up waiting on I/O from remote. So our goal is to keep these GPUs busy and utilize them efficiently. So to address the challenges that I mentioned, we have built Quiver, which incorporates a domain-specific intelligence of deep learning training at the caching layer. It is hash-based distributed cache, which allows secure reuse of data. It is co-designed with deep learning framework PyTorch. And Quiver also dynamically manages the cache space by allocating it to data sets which benefit the jobs the most. So finally, we show that Quiver can improve the throughput of a GPU cluster by up to 2.3x. So the rest of the talk is structured as follows. I just spoke about the introduction and motivation of our problem. Now I'll give you some background on deep learning training jobs. Then I'll speak about our design and implementation. And finally, I'll show you some results. So let's get some background on deep learning. The goal of every deep learning training job is to learn a model to represent the labeled input training data. The way it does this is by looking at millions of random subsets of the input training data called mini batches. The size of each mini batches is typically between 32 to 1024. And the deep learning training job then applies stochastic gradient descent on each of these mini batches. So every training job goes through phases called epochs, and in each epoch, the training job goes through the entire data set in different random order. So these jobs typically run for hundreds of epochs, spanning several days. So there are many frameworks to write such deep learning models like PyTorch and TensorFlow. So recall how we saw when multiple jobs access the same data set from the remote store, there will be excessive bandwidth load on the networking stack and the storage services of the cloud provider. Therefore, caching is a natural solution. Turns out the workload is also cache friendly. So I just said that every job consumes the entire data set multiple times and during each epoch. So if you cache the entire data set, there will be intra-job reuse. And another scenario that I mentioned was hyperparameter tuning, where people launch hundreds of instances of the same model consuming the same data set with different parameters. So if you cache the data set, there will be inter-job reuse as well. And finally, there are some popular data sets like ImageNet, which multiple models and multiple users use to run their jobs. So if you cache popular data sets, that will also lead to benefit. So however, there are some challenges in building such a cache. So the first challenge is random access. So as I mentioned, every job goes through the entire data set in different random order. So if the entire data set cannot fit in the cache, there will be a cache thrashing. And therefore, we can't just go ahead and use traditional caching algorithms like LRU. So the second challenge is job heterogeneity. Not all jobs need caching, and not all of them benefit the same from caching. So this needs to be accounted while allocating cache to each data set. The third challenge is security. Since the cache will potentially be shared across multiple jobs and multiple users, the access to such a cache needs to be secure, and we should make sure that the data will not leak to jobs which don't have access to. So we've designed Quiver using domain intelligence of deep learning at the caching layer to address these challenges. So the first challenge that I mentioned was if your entire data set cannot fit in the cache, the random nature of the I/O will lead to cache thrashing. So let's look at how we can have thrash-proof caching even when only a part of the data set can be in the cache. From an I/O perspective, only two properties need to hold for a deep learning training job. The first property is that each input element needs to be touched only once during an epoch, and every mini batch needs to be randomly sampled from the unused set of inputs. So what does this mean? So this means that I/O is substitutable. So instead of looking for some particular random set of unused inputs, any random set of unused inputs that are already in the cache can be returned. So this way, substitutable hits can significantly improve caching performance, even only a part of the data set can be in the cache. So let's look at this in more detail. So today, if a deep learning job wants a mini batch of size X, the default sampling of any deep learning framework will randomly pick X unused indices and returns it. Quiver, on the other hand, does a bigger lookup, say 10x indices, and then returns whatever x indices was in the cache. So consider this scenario. Here only 1/3 of the data set is in the cache, and the deep learning training job in this example wants a mini batch of size 3. So the default sampler would just pick any 3 unused indices, and as you can see, this will lead to only 1 cache hit and 2 cache misses. So Quiver, on the other hand, in this case looks up, say, for 9 indices, and it ends up getting 3 cache hits and 6 cache misses, and it returns whatever 3 indices that it could find in the cache to the deep learning training job. So the second challenge that I mentioned was how different jobs benefit differently from caching. So this depends on the amount of time the job spends on compute per mini batch. So if the job spends a lot of time on compute on every mini batch, the time spent on I/O for the next mini batch can be overlapped and pipelined. So interestingly, time per mini batch is across many mini batches in the deep learning training job is easy to measure, and it's similar and it's predictable. So this provides as a cheap profiling mechanism to measure the job's performance and different dataset caching modes. So benefit-aware caching using predictability works in 2 steps. First, every job measures total time per mini batch, including I/O and compute, under different caching scenarios of the dataset. And second, given a total cache space budget as the dataset sizes and the time per mini batch in different caching modes across different jobs, one can easily determine how to cache each dataset and what strategies to use. The third challenge that I mentioned was security, how the cache is shared across multiple models and multiple users, and how it needs to be secure and should not leak data. The cache servers need to provide data reuse and sharing while still retaining isolation. So to solve this issue, we address each file by its hash, say SHA-1, instead of its name. So for example, here 2 users have the same file in different storage accounts. So before performing any caching operation, the hash of the file is first computed and then the cache operations are performed. So this way, even with different users, different storage accounts, and the same files will end up with the same key. The mere fact that a person can compute the hash of a file determines that she actually has the access to the file. So now let's look at design aspects of Quiver. So Quiver has 3 main components. It has Quiver cache server, it has Quiver cache client, and cache manager. So cache server is a distributed service that runs on every virtual machine of the cluster and is a key value store. And it runs in its own privileged container, which the containers on the deep learning training jobs cannot access. And Quiver cache client is co-designed with PyTorch and is tightly integrated with the PyTorch data layer. And it performs substitutable hits that I just mentioned. So then we have a Quiver cache manager, which also runs on the same cluster in a different container. And it is responsible for benefit-aware caching using predictability and coordinated cache eviction. I'll talk about coordinated cache eviction later. So a typical scenario in any organization is to have a cluster of virtual machines with GPUs, which are dedicated to run deep learning jobs submitted by its users. Every job submitted to such a cluster runs in its own container. So Quiver, when deployed on such a cluster, can operate in 2 modes. It can be deployed as a single instance on the entire cluster, or Quiver can be deployed as a single instance per rack in the cluster. The latter will be useful when you want to avoid cross-rack I/O and you want to have a per rack copy of every file. So we saw what's the architecture of Quiver and how it can be deployed. Now let's see how it can be accessed once it's deployed. So as I just mentioned, Quiver cache client is integrated with PyTorch's data layer. And since the cache servers are all content addressed, so the cache client needs something called as hash digest to talk to the content addressed cache servers. And the notion of substitutable hits and cooperative mishandling is incorporated into the cache client. So I've already spoken about substitutable hits. Now I'll talk about hash digest and cooperative mishandling. So as I just mentioned, the cache clients need access to the hash of every file to talk to the content addressed cache server. So we represent the entire dataset by a hash digest, and every entry in hash digest has 2 major components. One is the hash of the file, and the second one is the location of the file. The cache client uses the hash of the file to talk to the cache servers, and it uses the location of the file to fetch the file from user storage account during a cache miss and then write it back to the cache servers. Finally, the entire key space is partitioned evenly across all the available cache servers. So in this example, there are 5 files and 2 cache servers. All the files with even hashes are stored in cache server 2. All the files with odd hashes are saved in cache server 1. So as I just mentioned multiple times, the common scenario in deep learning is hyperparameter tuning, where hundreds of jobs are launched of the same model which consume same data set. And remember that these jobs consume the same data set in different random orders. So this unique random nature of the I/O allows implicit sharding of the dataset and seamless sharing of cache misses. So as and when jobs progress, they get benefit not only by the files that they have filled in, but also the other jobs that have used the cache. So let's look at an example. So here there are 2 jobs and there is a data set of size 6. Because of the random nature of I/O, both the jobs end up filling different parts of the data set into the cache, and as they progress, they benefit from each other as well. So whatever I mentioned, like the cooperative mishandling, will be very useful if the entire data set can fit in the cache. So what if the entire data set cannot fit in the cache? There will be cache thrashing because of the random nature of I/O. So cooperative cache mishandling alone will not be enough. So to address this scenario, we use coordinated eviction with substitutable hits. So what we do is we divide the entire data set into, say, 10 chunks, and we use double buffering to make sure that only 2 chunks of the data set is in the cache at any time, and all the jobs operate on the same 2 chunks. So now that we can accommodate only 2 chunks of the data set at any given point of time, we need to evict them. So the eviction happens in 2 steps. First, the chunk is marked for eviction, and then the chunk is actually evicted. This is similar to Unix's unlink call. So no new reference to the chunk will be issued once it's marked for eviction, but however, every job which is already accessing it can continue to access it. So let's look at an example. So here there are 2 jobs and there are 3 chunks of the data set, and the job 1 and job 2 start using first chunk of the data set, and then they are done using the first chunk, and then they start using second chunk. And at this point, chunk 1 is marked for eviction. And there is a new job that starts at this time, and if you can notice, it started using chunk 2 instead of chunk 1, and because chunk 1 is already marked for eviction. And then job 1 and job 2 are done using chunk 2, and job 3 is still using, but even though if chunk 2 is marked for eviction, as job 3 got reference before it was marked for eviction, it can continue to use it. So this process continues. So now let's look at implementation and evaluation. So Quiver cache client is integrated into data layer of the PyTorch, which has roughly 3 parts: the data loader, data set, and sampler. And Quiver cache server is a C++ key value store. And Quiver cache manager is a Python program which intelligently allocates cache based on the benefits each of the data sets provide. So all the results that I'll be presenting right now are performed on a cluster of 12 virtual machines. 6 of these virtual machines have 1 generation of GPUs, the other 6 have another generation of GPUs. And we use 3 different workloads to evaluate. The first workload is ResNet 50 on ImageNet dataset. The second workload is Inception version 3 on OpenImages dataset. The third workload is Deep Speech 2 on LibriSpeech dataset. So I just mentioned that if the entire data set cannot be cached, we force all the jobs to operate on only, say, 2 chunks of the data set at a time. A natural question that arises is, will this impact accuracy of the deep learning training jobs? So here we can see that there are 2 different workloads which we have evaluated this on. The graph is ResNet 50 on ImageNet. The x-axis is the number of epochs, and the y-axis is the validation accuracy. The orange curve is Quiver, which operates on only 2 chunks of the data set at a time, and the blue curve is the default sampling mode, which does global random sampling. So as you can see, both the curves overlap, and both of them lead to the very similar final accuracy. And the second workload is Deep Speech 2 on LibriSpeech. Here there is something called as word error rate, and lower is better. So with baseline sampling, that is global random sampling, the model converges to a word error rate of 22.29, and Quiver, on the other hand, which does sampling within 2 chunks at any given time, also leads to very similar word error rate. So let's look at how much gains does Quiver provide. So here is a graph wherein the x-axis is the time in seconds, y-axis is the aggregate number of mini batches that are processed, and there are 7 ResNet 50 jobs operating on ImageNet dataset on 7 virtual machines with 4 GPUs each. So the black solid line is when there is no cache involved. All the jobs read data from Azure Blob Object Store directly. And the line in the middle is when only part of the data set is cached. Here it's 20%. And finally, the line with the highest slope is the scenario when the entire data set is cached. So as you can see, Quiver can provide significant gains like around 2.3x even when only part of the data set can be cached. The same thing can be observed in the remaining 2 workloads as well, Inception and Deep Speech 2. An interesting thing here to look at is Deep Speech 2, where it works on LibreSpeech dataset, and as you can see, if the curves of completely caching dataset and partial caching dataset are very close together. So this is one thing that we exploit while allocating cache space, so which we'll see in the next slides. So let's look at coordinated eviction in action. So here is a graph where x-axis is the aggregate number of mini batches, y-axis is time in seconds, and each vertical line is the lifespan of a given chunk. And here we run ResNet 50 again on ImageNet dataset, and the dataset is divided into 10 chunks. At time 0, we start 4 jobs consuming ImageNet dataset, and as you can see, if you draw a horizontal line on this graph at any given point, you can see that only 2 chunks are cached at a time. And at time around 1000 seconds, we start 3 new jobs. So here, instead of those jobs starting to use the first chunks, they start using what is already in the cache, that is third chunk in this case. So now let's look at benefit-aware caching. Here we have a mixed workload. We have 12 different jobs running on 12 virtual machines of the entire cluster. So we have 4 ResNet 50 jobs running on ImageNet dataset, 4 Inception v3 running on Open Images dataset, 4 Deep Speech 2 running on LibreSpeech dataset. So in this graph, the x-axis is time in seconds, and the y-axis is factor increase in throughput. So the baseline we compare against is where there is no cache at all. And in this case, we also compare it to LRU caching. And in this particular graph, the cache size we used was 100 GB. And the line on the lowest end of the graph is cache miss. And the line that is right above that is LRU. And the line at around 1.6x is Quiver. In this case, Quiver can intelligently allocate cache space. So it decided to run all the 3 jobs by caching only a part of dataset for every job. So as you can see, even with the tiny cache, Quiver can provide a significant throughput increase. So the same experiment we repeated with 200 gigabytes of cache size and 700 gigabytes of cache size. In 200 gigabytes cache size, Quiver decided to completely cache ImageNet dataset, which is around 150 GB, and it decided to run the other 2 datasets in partial caching mode. Finally, we have a 700 gigabytes scenario. Remember that the entire dataset size is around 780 GB. So here, although LRU comes close to Quiver, there is still some cache thrashing due to the 80 GB dataset size gap. So therefore, Quiver improves cluster throughputs anywhere between 1.6 to 2.3x, depending on the cache size. So to summarize, Quiver is a domain-specific storage cache for deep learning training jobs. It utilizes I/O behavior of deep learning training jobs at the caching layers, and substitutable hits and predictability are some of the things which you can do only by incorporating domain-level knowledge. And we show that it can improve the GPU cluster utilization by reducing I/O wait time. Yeah, I'm happy to take questions now.
I'm Umesh Maheshwari from Hewlett Packard Enterprise. You mentioned that each mini batch is selected randomly.
Yes.
I'm guessing that it's pseudo-random in that there's some random seed, and from then it's very predictable. So
no,
it's not.
It's not like random seeds are used only while debugging like accuracies. So when you do hyperparameter tuning, if you want random seed to be there, you can turn off cooperative caching and run on global sampling.
I see. Okay. I was about to say that if it's predictable, then one could use prefetching based.
No, the more random it is, the better it is for convergence, for stochastic gradient descent.
Right. It could be random yet predictable. So if it were to be predictable, were not to be influenced by how the epoch is going, then I'm guessing
ideally,
that's not
for every epoch, the order of in which you see inputs needs to be different, so it won't be very, very predictable, and it should be different across the jobs as well.
That could still be provided with a pseudo-random sequence. Okay, anyway, I was just wondering whether prefetching could be, the knowledge that you're going to access.
That is sort of what we like. If you force them to operate on only one part of a data set at a time, like you're restricting the randomness to only that.
Okay, maybe we can talk later. Thanks.
Song Jiang from UT Arlington. Looks like the efficacy of your design depends on how many training jobs at the same time use the same data set, right? Yeah. So in practice, is this a case? Many users use a shared system that just do the modeling, that you use the same things, same data set at the same time?
It's not about many users using the same model and same data set. It's that hyperparameter tuning that I mentioned, wherein people run the same hundreds of instances of the same model. It's consuming same data set with different parameter configurations. So that is a very common scenario in deep learning.
Okay.
Yeah.
Vasily Tarasov, IBM Research. So in the beginning of the talk, you were talking that all of the data is in the object storage. Then you use the term file in many cases. So it seems that Quiver kind of implicitly converts object access to file access. So I was wondering how generic it is. So for example, if a user decides to remove a file or rename a directory, if object names are separated by a slash, does it anyhow propagates back to the object storage, or it's just locally cached?
So the location of each file is in the hash digest file, like I mentioned. So if you change any structure there, you only have to change your digest file. Mm-hmm. So that way you can decide to use any storage structure you want.
Mm-hmm. Yeah. But so let me kind of, maybe a related question, but slightly different. So the result of the training, for example, the model, where is it typically saved in this case, in this pipeline?
Result of what?
Of a training.
You mean the model parameters.
Mm-hmm.
So that user can decide to store that anywhere. We don't.
You don't touch it at all?
We don't touch that.
Okay, thanks.
Thank you.
Yes, Kevin Harms, Argonne National Lab. I wanted to better understand the substitutable hits. Okay. So the idea there was you were trying to prefer entries that were already in the cache.
Yes.
So I think you kind of saw some of this by you're sort of changing the randomness of the problem, so you're preferring some data that you already have cached. Yes. So that's going to affect the overall training result. Did that bother you, or is that something you tried to address?
So yeah, that is one of the results that I showed, right? So
correct.
If you see this graph, at least in our experiments, it didn't show up.
And also, can you just clarify that? Because in the picture you drew, it's like you could assume that you're only ever going to look at like 1/3 of the data. You're never going to look at all the data. And so convince me that you're actually going to look at all of the data, or given, so convince me, because it's still a little bit fuzzy.
Over the entire epoch, we look at all of the data. Yeah. So because I also mentioned we do double buffering, so as and when the chunks in the buffer move, you end up looking at the entire data set.
I have one question. I have one question too. How generally or broadly do you think you could apply these same techniques, say, outside of deep learning? So for other ML techniques, or maybe things outside of ML? So
I think the partial caching can be used in most, like in workloads wherein the order of the input doesn't matter. So one thing we exploit here is that as long as the mini batch ordering is random, it doesn't affect too much if you randomly sample from the entire global data set or what is in the cache. So if your workload can accept inputs like that, I think you can still use it.
All right, thank you. Let's thank our speaker again.